Hi, welcome to Online Lecture 2 on Substituents. Here are the topics that we're going to be covering in today's lecture. So let's start by talking about substituents. A substituent is essentially any group that's attached to the backbone of a molecule. And if you'll remember from last online lecture, the backbone is essentially the longest chain or ring in a molecule. When you're coming up with the name of a molecule, in order to make the name unambiguous, which is the goal of IUPAC, we have to make sure that we specify the location on the backbone of the substituent. So let's look at an example. What is the carbon index of NO2 on this backbone? So as you can see, the longest chain is 5 carbons long. It's the zigzag. And then coming off of that is an NO2. And so the carbon index is essentially just numbering all the carbons on the backbone and finding the location of the substituent. So when we number these carbons, we essentially find NO2 on carbon number 4. However, when you number the carbons, the goal to come up with an unambiguous name also requires that you number all the carbons so that the first substituent that you encounter is on the lowest possible index. So essentially, if we number this carbon chain in reverse, then the substituent is on number 2 instead of on number 4. So that is the optimal way to number this carbon chain. And so the carbon index of NO2 is actually 2. So just like last lecture, when we looked at the simplest form of organic molecule, which was an alkane, we're going to start with the simplest type of substituent, and that's called an alkyl. And an alkyl is essentially just a substituent form of an alkane. So what does that look like? It has to be a straight chain, just like an alkane does. And then to name it, you just replace ane with YL or eel. So let's just start with an example. Let's name this compound. So when we're looking at this compound to name it, we have to find the longest backbone chain. So it's not necessarily the 4 carbons that are horizontal. If we start at the top, we can actually count out the longest chain as being 5 carbons long. And so the root of this name is actually pentane. The substituent that's coming off of carbon 3 is a methane because it's 1 carbon that's coming off of the main chain. So we would change that to methyl. So we would call this molecule methyl pentane. And again, in order to make sure that the name is unambiguous, we have to place the methyl on a specific carbon number. So either way, if we number it from top to bottom or bottom to top, the methyl is on carbon number 3. So therefore, we have to add 3 to the name. And the way that we do that is we essentially separate the index from the name by a hyphen. So we're going to write 3-methyl pentane, and that's the full name. And just like we have alkyls, you can also have a cycloalkyl, and that's essentially the substituent form of a cycloalkane. So to name that, you do the same thing. You just replace ane with eel. So let's just dive straight in and look at this example. So in this case, the longest chain is the horizontal chain, and that's 6 carbons long. So the root of this compound is hexane, and then the name of the substituent is cyclopropyl. It would be a cyclopropane because it's 3 carbons in a ring, and then it's cyclopropyl because it's a substituent. And then this is on location 3, so we add 3 to the front of the name, like that. So let's look at the next simplest type of substituent. And those are essentially just halogen atoms that attach to a carbon chain. So we call them halo groups. And the way that we name those is essentially just by taking the name of the atom and then shortening it into a prefix. So for example, fluorine, when attached to a carbon, is called fluoro. Chlorine is called chloro. Bromine is called bromo. And iodine is called iodo. It's really that simple. And when we're adding halogens to a carbon backbone, it essentially just takes the place that a hydrogen would take, because nothing else attaches to a halogen, just like nothing else attaches to a hydrogen, because both of those have a full outer shell. So let's jump into a couple examples. So here we have a chlorine attached to a hexane. So we'll start with the root, hexane. Its substituent is chloro, and then that is on carbon location 2, if we number from left to right. In the second example, I'm just going to write this whole name from left to right. So the substituent is fluorine, and we know in order to get it to be the lowest index, we want to start the numbering at the right. So that would be on the very first carbon, so it's 1 fluoro, and then there are 4 carbons in this chain. So it's 1 fluorobutane. Another common substituent that you might encounter is called nitro, and that's essentially just nitrogen dioxide attached to a carbon chain. Just to be clear, it does not refer to NH2 when it's attached to a carbon chain. That's another common one, and we're not going to go over that one yet. So let's just start with an example. This one's pretty straightforward. If we have a carbon chain with a NO2 attached, we would just write 2 nitro, and then it's 5 carbons long, so it's pentane. It's really that simple. Let's try another one. Draw, so this time we're starting off with a name and we're going to a draw. So draw 1 nitrobutane. So I would start by drawing the root or the backbone, butane. So that's 4 carbons long like this. And then 1 nitro. So that implies that the NO2 is at the end of the chain. And it's equally correct to draw it at the left or the right. So I'll just draw it here on the right like that. And that's the molecule. So next, let's talk about alkoxy groups. That's essentially when you have an oxygen connected to your backbone and then a carbon group coming off of that oxygen. So this is essentially deriving its name from the alkyl chain attached to the oxygen. And we just replace the YL, so of the alkyl, with oxy. So an example you might find, here's one, draw 1 ethoxypropane. So again, let's start with the root. We have propane, so a 3 carbon chain. And then what does an ethoxy look like? So the O is connected to the end of the chain because it's 1. So attach the O here. And then eth implies that there's an ethyl on the other side of the oxygen. So just add 2 carbons on the other side. And that's essentially it. So let's try another example. So what is the name of this compound? So let's start by looking, so the longest chain is not a chain, it's actually a ring. So we have to choose between the triangle and the pentagon. So the pentagon has more sides. So the root of this is cyclopentane. And then the substituent name is derived from the oxygen and then the alkyl group coming off. And the alkyl coming off of the O is actually cyclopropyl. So the full name of this compound would be cyclopropoxy cyclopentane. This substituent would be on location 1, but I don't actually have to write location 1 because adding the index is not necessary to make the name unambiguous. Why is that? Because no matter where we put that substituent around the cyclopentane ring, we would always start the numbering there. So it would always be location 1. So in instances where the index is not needed to make something unambiguous, you actually don't have to write it. But there's nothing incorrect about writing the index. So if you're uncomfortable with making that call, you can always write 1 cyclopropoxy cyclopentane. That's equally correct. And so we're going to encounter this type of molecule a lot where there's an oxygen surrounded by 2 carbons. That's typically referred to as an ether in the organic chemistry community. But that's not the official IUPAC name, so therefore I'm not going to teach you how to name those. But if you encounter the name ether, that's what it's referring to. So what do